Now, that was just an introduction, kind of an example where it's not clear if there's a relationship between the explanatory and the response variable. So just to give an idea of when we would use the chi-square test, but now on this page and the coming pages, we'll actually get into what is the chi-square test, how does it work, what do we do? Like I said, we'll continue our discussion of the chi-square test for independence for the variables gender and body image in the population of U.S. college students. So we stated the null and alternative hypotheses. The null was that there is no relationship between gender and body image for the U.S. college students. The null says that the variables are independent, but the alternative hypothesis says the variables are dependent. In other words, there is a relationship between gender and body image for U.S. college students. The second step after stating the hypotheses was we analyzed the data. There were 1,200 college students polled on this, 440 males and 760 females, and we said, give us a description. What do you think? Are you about right, overweight, underweight? Anyway, and then a bunch of percentages were calculated. This many females out of the total number of females thought they were this, and this many males out of the total number of males thought they were that. And then total people, how many people, male or female or whatever, and thought that they were each category out of the total number of people. If the variables are independent, the percentages of males and females with a given response will be the same or at least close. But that's kind of a relative term, I should put that in quotations, at least close. So how close is close? How do you think within 5% is close? Or 10% or 1%? What are we talking about close here? Previously, we determined that in our sample, there are differences in the percentages of males and females who answer about right, overweight, or underweight. But I feel like in my mind, the percentages were close enough to the total percentages that it's hard to say if there's a relationship or not. So this is a good example of when we would need the chi-square test to see if there really is a relationship. If the gender and the body images are independent, then percents in a response variable category are the same. We need to determine if these differences are typical in random samples, because it might just be this sample of 1,200 college students just happened to have this. By random chance, we got more females who said they're overweight than males, or more than the total. But we need to do this test to see if this is kind of like just due to random chance, or is it actually this represents the whole population, and female college students feel more one way than male college students, so gender really does affect body image. Then where gender and body image are independent, perhaps the differences we see in the sample are just fluctuations expected in random sampling, like we said, or perhaps these differences are too large to be explained by chance when the variables are independent. We will not know until we complete the hypothesis test. So third step, we're going to assess the evidence. In this part of the hypothesis test, we find the test statistic and use it to find a p-value. Of course, we will also need to learn the conditions that allow for the use of a probability model. The chi-square test statistic compares the observed counts with expected counts, where the expected counts are what we expect to see when the null hypothesis is true. The variables are independent. Before we introduce the formula for the chi-square test statistic, we will examine what we mean by expected counts, quote unquote, in more detail. We'll talk about calculating expected values for a test of independence. Expected counts always describe what we expect to see in a sample if the null hypothesis is true. In this situation, if gender and body image are independent, then we expect the percentage of students who answer about right in the sample to be the same percentage of male or female students who answer about right. Similarly for overweight and underweight responses. Therefore, to find the expected number of a group with a given response, we multiply the group total by the baseline percentage for that response. Here are the calculations of expected count for the response of about right. We'll scroll down and look at that now. Okay. So in this sample, a student will answer about right 71.25% of the time, because the total number of people who said about right, whether male or female, were 855 divided by the total number 1,200. That was a percentage that was in that table. So if gender does not impact the student's perception of personal body weight, i.e. the null hypothesis is true, then we expect 71.25% of females and 71.25% of males that will answer about right. Now let's look at the expected count of females. In the sample who will answer about right, it should be about the same. Yeah, 71.25%. So 71.25% of the number of females, that's what we're calculating here. 71.25% of the number of females. We just multiply the decimal form of that percent, by the number of females. So 71.25% is in decimal form 0.7125. Multiply that by the number of females, and you should get the expected number of females who would say this is for about right. The expected count of males, the same percentage, we're expecting the same percentage of males to say about right. If the gender has nothing to do with body image, that percentage in decimal form multiplied by the number of males, 440, is 313.5. So this is what we should see if that percentage, 71.25, is true for males and females, or something close to that. Here are the calculations of expected count for the response of overweight. So same kind of thing. In the sample of a student will answer overweight 19.58% of the time. That was the total of all the students, male and female. It was 19.58%. So if the null hypothesis is true, that gender does not affect body image, then we expect that percentage of females and that percentage of males who will answer overweight. So we'll do a similar calculation where we take that percentage, 19.58, put it in decimal form, multiply it by the number of females in the study, 760, and get the expected number of females who will say overweight. And then, the expected count of males to say overweight would be the same percentage in decimal form. The 19.58% in decimal form is 0.1958 times the number of males was 440. So we should expect 19.58% of the 440 males to say that they feel they are overweight. 19.58% of 440 is 86.2. So, okay, we'll pause to practice finding expected counts before we continue with the formula for the chi-square test statistic, because it's not super obvious how to do that, and it's not clear. It's good to test or practice that first before we move on to the actual chi-square thing.